Hello everyone. In this video, I'm going to discuss about RLHF in LLMs. RLHF stands for Reinforcement Learning Through Human Feedback. LLM stands for Large Language Models. You would have experienced the impressive capabilities of LLMs. But let's recollect the functionality of LLMs. LLMs mainly predict the next word for a given input text. To be precise, they predict next token for a given sequence of tokens. This predicted next word is appended into the input text, and based on the new input text, another next word prediction happens, and so on until the end of sequence is reached and entire text will be generated. In short, LLMs take input text and they generate some output text. And these LLMs are like transformer based neural networks. Now let's look at LLM training. LLM training broadly involves pre-training, supervised fine-tuning, and RLHF. In case of pre-training and supervised fine-tuning, we have expected next token information from the dataset. We have predicted next token information from the model, and we can somehow calculate the loss, we can backpropagate the loss, and we can train the transformer model. This is more or less a supervised learning. But with RLHF, it is a bit different. The human feedback here contains just the preferences of humans who are generated LLM responses. Like LLM generates couple of responses for a given prompt, and humans were asked like to choose which response they like and which they don't like. And you can see there is no explicit expected next token information in this. If you look at some sample RLHF dataset, it looks like this. We have input text and couple of generated text, one of which is chosen and one of which is rejected by humans. This is a sample RLHF reward dataset which is available in Hugging Face. We have some prompt and chosen response and then the rejected response. For example, a given prompt like what are the pros and cons of electric cars? We have two responses generated by LLMs, and one is a preferred response by human and one is rejected by humans. Now we have to use such a simple data set containing human feedback, and we have to train the underlying LLMs. And you would have observed like there is no explicit next token information and it is different from supervised learning. Now, how do we train the LLMs using RLHF? LLM training involves three components. One is the data set containing human feedback, which we have already discussed, and we have reward model, and we have reinforcement learning. Let us see what this reward model does. This reward model is a transformer based model which gives a scalar reward for a given input text by taking into account human preferences. So this transformer based model should give a higher reward for sentences chosen by the humans compared to the sentences rejected by the humans. Once we have such a reward model, we use that scalar reward from the reward model, apply reinforcement learning and train the LLMs to align with the human preferences. Now, reward model training. For reward model training, the data set is the same data set, the RLHF reward model data set. It has the input text, generated text which is chosen by human, and generated text which is rejected by humans. We have to use this data set and train a reward model to give a reward according to human preferences. And you can observe here this data set does not contain explicit reward information. It just contains some preferences over the generated text, and we have to use that to train this reward model. Now, how do we use this reward data set to train the reward model? which will predict and give the scalar reward value. And like, what is the loss function to use? How do we calculate the loss, and how do we back propagate the loss and train the reward model? Reward model training requires modifying the transformer. We take the transformer, we take the logits of last generated token, pass it through few additional layers of neural network, and then get a scalar reward. Once we have such modified transformer, we take the input text and the chosen output text, pass it to a transformer, get a reward. Similarly, for rejected text, we get a reward. We pass those rewards to the loss function, and this is the loss for one data point. We calculate the loss for batch of data points, we backpropagate the loss, and then the training continues. If we see the loss function, this is log of sigmoid of reward for the preferred output minus reward for the rejected output. The sigmoid function values ranges from 0 to 1. Log of sigmoid function values ranges from minus infinity to 0. The total loss is minimized when it is close to 0. If you see in this loss function, there are no labeled rewards in the loss function. We only have the labeled human preferences. The reward here, both these rewards here are the rewards predicted from the model, and we only have the labeled human preferences saying that this reward should be greater than the other reward, which is the rejected reward. And once this loss is minimized, the transformer model predicts the rewards aligning with human preferences. And this loss function is based on Bradley-Terry model. You can check more details of this. Okay, now we have the reward model which gives a scalar reward. Now, how do we use this scalar reward and train the LLMs by applying reinforcement learning? Before getting into reinforcement learning, I wanna share some analogy with game of chess. In game of chess, we have an agent which makes sequence of moves, that is perform actions, and at the end the agent gets a scalar reward, that is win or loss. We make sequence of moves at each step, and towards the end we get a reward. We will know the end result, that is win or loss. We have to use this information and we have to try the neural network to play the winning games. But the winning games are not played just by random. The game is you can't win the game by just playing at random. At each board position, we have to train the trained neural network should predict the next best move, keeping the in order maximizing the final result, that is winning. So if you take the LLMs, we have a similar situation. LLMs keep generating sequence of tokens, and at the end of entire text, the reward model gives a scalar reward. We use this information and train the LLMs to generate text which is preferred by humans. And to do that, for a given current text, LLMs should know how to predict the next best token which aligns with the human preferences, and the generated end text will have a higher reward aligning with human preferences. For game of chess, this is done using reinforcement learning. So let's apply reinforcement learning to it and train our LLMs. Let us look at some of the reinforcement learning terminology. In reinforcement learning, we have environment and we have agent. This environment, we call it like state, and we have reward. We get rewards being in that state at timestamp t. The agent will have access to this information, and when at current state st, the agent will perform an action. By performing the action, the environment moves to a new state and it will have a new reward. The agent gets that information and performs the next action, and then the state will be changed and you'll have a new reward. So throughout this process, the agent should learn how to perform the best action so that the total reward which we get is maximum. Okay, so let us look at some of the terminology. We have in reinforcement learning, we have states, we have actions, we have trajectory. Trajectory is like when you are in a particular state, you take an action, you move to the next state, and in that state you take another action and all. That is called trajectory. And we have rewards and expected returns. Reward is the reward which we get at a particular timestamp being in that particular state. Expected return is the total return from that timestamp till the end. And we have value function. The value function is the total reward we get being in that state by following a particular policy pi. We have policy function which gives the action which to be taken at a given state. At a given state, what is the action to be performed? Okay. And with respect to the LLMs, the current input text is called the current state, and choosing or sampling next token from the list of available tokens, that is the total action space, and generating the sequence of tokens and generation of text, that is called as trajectory. And we don't have the immediate reward, we only have the final reward for the complete text which is given by the reward model. And we define a partial text. We have a value function which gives a reward value for the partial text, and we need to have the LLMs to choose the next best token for a given input text, or that is for a given state. Policy gradient algorithm. Let us look at this objective function. We sample the trajectories from a policy function, and we have a reward following that policy and expectation of reward over all such trajectories. Now we want to maximize this objective function. How do we maximize this? We calculate the gradient of this objective function and then perform the gradient ascent. In order to calculate the gradient of it with respect to theta, we have theta which is part of expectation, and we have theta which is part of this reward function. So we expand this term. Here, probability of a particular trajectory and a reward following that trajectory, and this is sum of all such trajectories. We'll take this gradient inside this integral, and if you look at this term, for this term, like we apply the log derivative trick and it becomes like this. Now we have the probability of that trajectory. We can make it a part of this expectation. Now we have the gradient of the objective function will be converted to this, and this is the final gradient of the objective function. It is the expectation of all the trajectories, and inside this is a gradient of log of the objective function and sum of the rewards from that timestamp onwards. Once we have the gradient of this objective function, we perform the gradient ascent. Vanilla policy gradient algorithm. It goes like this. We start initializing the policy parameter and the value function parameters, and we collect set of trajectories by running the policy pi, and we collect the data. We compute the rewards to go, we compute the advantage estimates, we estimate the policy gradient. This is the same thing which we saw in previous slide, and we perform the gradient ascent. And here, like, we adjust the parameters of value function here, and we repeat this whole thing k times until convergence. By using this vanilla policy gradient algorithm, we can optimize the policy function to give maximum rewards. In our case, we can train the LLMs to give maximum rewards to align with the human preferences. Learning to summarize from human feedback. This is the reference paper which I have used to explain RLHF. In this paper, they talk about reward model, and this is the loss function which is used to train the reward model, and we get a scalar reward out of it. And we consider the reward for the entire summary from the reward model, and we use this reward to in the PPO algorithm, which is a kind of policy optimization reinforcement learning algorithm. And here, if you see the total reward, they have added some regularization term over here. And to train the RL algorithm, we need reward model, we need policy, this is our actual LLM, and the value function. The PPO value function is initialized from parameters from the policy function. That's all. Thank you for watching the video. Hope you enjoyed the video.